All right, everybody, welcome back to statistics. We had just finished our section on looking at mean differences between or within data. Now for our last section, we're going to be looking at relationships in data, and you're going to learn two statistics in this section. The first starting with correlation. So what we're going to do in this video is we're going to look at correlation, specifically the correlation coefficient. We're going to look at something called scatterplots. We're going to talk about the concept of correlation versus causation. And then in the next video, we'll look at how correlations are applied in hypothesis testing. So as we always do when we start a new stat, let's just look at the basics of correlation and figure out how it works and what's going on at the bare level. So what is correlation? When you take correlation by itself, it's actually a descriptive statistic that's used to assess the relationship between two variables. So how it's doing that is it looks at the variances of the two variables, and it wants to see how much do the variances of the two variables overlap with each other. Because typically, if the variance of one variable as it changes, if the other one changes along with it, then that's an indication that those two variables might be related. Now, since correlation looks at variances that measurement of variability, the one that you have before you square root it to get standard deviation, you have variance, which requires continuous data. So when you are looking at relationships in data, specifically when you're dealing with correlation and linear regression, which you'll learn, that's the last stat you'll learn, you have to be working with continuous data. You're not working with categorical in this scenario. So when you're calculating a correlation, you are going to produce a number called a correlation coefficient. There's a few aspects to this coefficient. For one, it's standardized, right? It falls on a certain scale. The number is not just going to be anything. It's going to always fall on a specific scale that I'm going to show you. And the numerical range of the values represents the degree of relationship between the two variables. So let me help break this down for you. So correlation coefficient will always fall on a range of -1 to 1. Now 0 on this range indicates no correlation, meaning the variables are not related whatsoever. Now a correlation of +1 or -1 indicates perfect correlation, meaning that they are identically related. Pretty much the only way that that happens in real life is if you take a variable and correlate it with itself. Of course, it's going to be 100% correlated because it's the exact same numbers. So usually the number is going to fall somewhere between 0 and 1. Now, the further the number is from 0, either going to the right or to the left, indicates a stronger correlation, meaning a stronger relationship. So closer to 0 is closer to no correlation. Further from 0 is getting closer to perfect correlation. So close to 0, weak. Further from 0, strong. Now the notation that's used for the correlation coefficient is a lowercase r. So when you see r, that's always referring to a correlation coefficient. Now, why is it that we have a +1 and a -1? Well, it's because a correlation can be positive or negative. So let me break those down for us here. So positive correlation is when the variables are changing in the same direction. I like to use the example of you looking in a lobby of like a big fancy hotel, one where you can see the elevators on the outside going up and down. Positive correlation would be like when you're looking at two elevators side by side, and as one's going up, the other one's going up with it, and as it goes down, the other one goes down with it. They're kind of varying together, going up and down together. One may be lagging behind the other one, but they're moving in the same direction together. So that's indicated by the positive sign, or just by nothing in front of the number, right? A number that has nothing in front of it, we just know is a positive number. So if you see a positive correlation coefficient, that indicates that it's a positive correlation. Now, if you see a negative sign, that indicates a negative correlation, which means that the variables are changing in opposite directions. So it's one elevator's going up and the other one's going down with it. So they're moving in opposite directions. That's a negative correlation. So that's the two kinds of correlations you can get, a positive or a negative kind. So when you're looking at a correlation coefficient, the number, there's a few features you want to pay attention to. First is the sign. Is there no sign or is there a negative sign? No sign indicates positive, a negative indicates negative. That's the sign is telling you the direction of the relationship. Now the number itself is telling you the strength of the relationship. Remember, the number in relation to 0 tells you how strong it is. Further from 0 is stronger, closer to 0 is weaker. So take, for example, these two correlation coefficients I have represented for you here. Let's say that R equals negative 0.75, and then another one that R equals 0.56. If you're thinking of these numbers as just numbers like on a number line, obviously 0.56 would seem to be stronger than negative 0.75. But that's not how you would interpret a correlation coefficient. Negative 0.75 is stronger than 0.56 because negative 0.75 is further from 0 than 0.56 is. The fact that negative 0.75 is negative is not referring to its strength, but its direction. It's a stronger correlation that's a negative relationship. 0.56 is kind of a moderate relationship. That's a positive relationship. So that's how you will interpret R scores, as we'll call them, how you interpret correlation coefficients. Now, when visualizing correlations, this is a very helpful tool to kind of see how your variables are related to each other. The most common graph used to represent correlations is something called a scatter plot. They are also called scattergrams. They're used synonymously. I choose the term scatter plot, but it could be called scattergram. Now, the way that this graph works is it's a standard XY axis. And what you'll see on this graph is a bunch of little dots. Okay? Now, each dot is an intersection of an X score on the X-axis and a Y score on the Y-axis. So say that we have a pair of data. We have 3 on a 3 for an X score and a 2 for a Y score. What you would see is you would go 3 over on X and then up 2 for Y, and then you put a little dot on the graph. That shows the intersection of an X score and a Y score. Now, you'll see a lot of dots. A data point will be, every data point represents a pair of X and Y scores. And so however many X and Y scores you have, however many pairs you have, that's how many data points you would see. Now, it's the shape of the data points that kind of tell you about the relationship. The closer the dots are together, the stronger the correlation. The further they are from each other, the weaker. Now, a second thing you can look at the shape of it is if the dots look like they're kind of grouping up in a linear fashion, kind of like a line. And if you see that the dots seem to be moving in a line going upwards from the left, then that indicates a positive correlation. Now, if it looks like the line is going downwards from the left, then that indicates a negative correlation. So let's do some practice here so we can see how this works. So let's say that I have a set of 7 X scores and 7 Y scores that I've shown you here. And I've went ahead and plotted them on the standard XY axis. So take the first pair. X is 2, Y is 3. So the first dot, I go over twice on the X-axis, and I go up 3 on the Y-axis, and you get your first data point. And you can do the same thing with the rest of the pairs of data. Now you can see that they're kind of grouped together. They're not far apart, so maybe this is not a weak relationship. They're not tightly packed, so maybe it's like moderate to strong. And you can see that the dots are kind of moving upward from the left. That indicates a positive relationship between X and Y here. Now this slide here, I've shown you some more visuals of just some hypothetical scatter plots, and you can see them with the correlation coefficient. So you can see how a scatter plot would look with that particular coefficient. Pause the video for a second, look over these graphs. Now, the one I want to draw your attention to first is the one on the bottom right. So a correlation coefficient of 1, that's a perfect relationship, right? What you would see is that X and Y values are lining up perfectly with each other. So that would produce a perfect straight line where every dot falls in line with the next dot. Now, look at the one just to the left of it, of a correlation coefficient of 0.90. You can see that it's very close to perfect, but not quite. So the dots are very close together, but not in a straight line, indicating that a very strong relationship, positive relationship, is they're moving upward from the left, but not perfect. Now, if you look to the one just to the left, on the very left on the bottom, that's 0.5. That's about right in the middle, moderate relationship and still positive because the dots are moving upwards to the right. Now, if you just jump above that graph, the top left one, you have negative 0.90. So again, almost perfect, but the dots are moving downward from the left. As X is increasing, Y is decreasing, which is why the dots are going downward in that fashion. So a negative relationship. And then I want you to jump over to the upper right one. That one is 0, correlation of 0, means no relationship. That means the dots are going to be spread out and there's going to be no direction that you can interpret. It just looks like they're all spread out circularly or just in a blob. There's no upward or downward trajectory for them. So that would be an example of what no relationship looks like on a scatter plot. So the visuals here are very helpful to help kind of get a visual glance at what the relationship between your variables looks like. But we always want to go back to the correlation coefficient, right? So let's learn how we can actually calculate this coefficient. So the way that you would calculate it is you calculate R using the top part, which is called covariance, divided by the bottom part, which is the standard deviation of your X variable times the standard deviation of your Y variable. Now, an R-score, as I said earlier, represents the standardized degree two variables vary together. It's always standardized. It's always going to fall on a range of -1 to 1. Now, the top part of this equation is covariance. This is the number that's actually representing how much the variances of your two variables overlap with each other. And now, it's going to be in the format of whatever numbers the variables are in. If the X and Y variables are in the hundreds, the covariance will be in the hundreds, right? Because it's just the raw score. It hasn't been standardized. So that's why the bottom part of covariance is the standardization. So you would take the standard deviation of X and Y, and you divide covariance by that, and that's what standardizes the covariance onto that scale of -1 and 1, and you get that R-score there. If you get an R-score and it falls outside of -1 or +1, then something went wrong in the calculation. Standardization will always make the covariance convert to a scale of -1 and 1. So now we have to see how we can calculate covariance, so that way then we can calculate our correlation coefficient. So let's say that we have this scenario here. We have 5 people. Actually, let me back up and say this. Let's say that you are at a party, and because you're taking stats, you are just very attuned to statistical things in your environment these days. So you take notice of how many times people are smiling and how many people are coming up and talking to those individuals. So let's say that you choose to observe these 5 people here. You got Jerry, Elaine, George, Newman, and Kramer. And so you're looking at, for each person, how many times they smile throughout the duration of the party. And then you also are taking count of how many people are going up and talking to them. And you want to know, is there a relationship between how much these people smile and how many people come up and talk to them? So what we have a few things that we can calculate here, so we can put things together. We have to take the sum of X and the sum of Y. We have to take the standard deviation of X and the standard deviation of Y. We have to take the products of X and Y for each person, and then we have to sum those together. Once we have all those ingredients, we can begin to fill in the equations here. So covariance, which I've already shown you here, is we can take 84, the product of the sum of the products of X and Y, minus the sum of X times the sum of Y divided by N being the sample size. We got 5 people. Once you get that top part of the covariance equation, you take the bottom part, which is N minus 1. 5 minus 1 is 4, so the top part divided by 4, and you should get a covariance of 3.75. Now with that, we can plug it into the R equation, take your standard deviations and plug them on the bottom, and then go ahead and try and calculate the R-score for yourself. So if you've got that number, let's see if you got it right. The correlation coefficient you should have calculated, the R-score is 0.879. So that is the correlation that you should have got. That is representing how much smiling is related to being talked to. So once we get the correlation coefficient, what we have to do here is now interpret what it's telling us about the relationship between smiling and talking. So first thing we interpret is, how strong is it? How strong is a correlation of 0.878? Now, one technique that some people use is they kind of just have a range of strengths, kind of that I can show you here on this table. And whatever range your correlation fits into, you just say, well, okay, then it's that strength. So, like for example, 0.2 to 0.4 is weak, 0.6 to 0.8 is strong, 0.8 to 1 is very strong, so on and so forth, right? So 0.878 obviously falls between 0.8 and 1, so we might say very strong. Here is the problem with measuring strength using this arbitrary range system here. Let's say hypothetically that I got a correlation of exactly 0.80. How would you know if it falls into strong or very strong? Or how about this? What if I got a correlation of 0.79? Obviously would fall in the strong range, but is 0.79 that different from 0.81? Because 0.79 would be strong, 0.81 would be very strong, but they're almost the same strength. Just look at how far apart they are. They're just 0.02 points apart. So this is arbitrary. It's not very clear and precise, and we always want to be precise when we're doing statistics. So we're going to do a better way of interpreting the strength of a correlation. So the better way to do it is using something called the coefficient of determination. So this will tell us how similar the two variables' variances are. It actually more specifically tells us how much of y's variance is accounted for by x's variance. How much of their variances overlap with each other. Now the way that you do this is you simply take your r score and you square it. So the result is just simply called r squared. So r squared is the coefficient of determination. This tells us how strong our relationship is. The bigger r squared, the stronger the correlation. Now, on the flip side, you can also calculate something called the coefficient of non-determination. Let's say that you wanted to know how dissimilar the two variables' variances are. You want to know how much of y's variance is not accounted for by x. Simply what you do is you just take your r squared and you subtract it from 1, right? Because 1 is the max that it could be. So 1 minus r squared gets you your coefficient of non-determination. So let's give this a shot here. So take the correlation coefficient and square it to get the coefficient of determination, and then subtract it from 1 to get the coefficient of non-determination. Now, if you did that, what you should have gotten is an r squared of 0.772 and a 1 minus r squared of 0.227. If we just kind of round these and turn them into percentages so we can talk about them a little easier, we could say that based on the coefficient of determination, we know that 77% of y's variance, 77% of being a top 2, is accounted for by smiling, x's variance. And 23% of being top 2 is not accounted for by smiling. So if we were to ask how strong is this relationship between smiling and being top 2, it's about 77% strength. The 77% of their variances overlap, which is quite a large amount. That's 3/4 of their variances overlapping there, compared to 23% of their variances not overlapping. So that's how you would interpret a correlation coefficient in regards to strength. Now the direction is obvious by the sign. This is a positive correlation, so we know that as the more that you're smiling, the more that you're being talked to, and we know that that's happening around 77% of the time, you might say. Now, the last thing I want to cover in this section is distinguishing between correlation and causation. And I want to use a couple funny examples for you that are actually pulled for some real data gathered that are available in certain public data sets. So let's say that you came across an article that in big letters said, eating cheese will kill you. And you might think to yourself, well, what else is new? Everything kills us these days. But let's say that you're really interested in reading on of like, why is it that cheese will suddenly kill me aside from cholesterol and all that? So let's say that you then are presented this graph that shows the per capita cheese consumption, which means how much cheese is being consumed in a certain economic area. And you see that it's positively related with the number of people who have died by becoming tangled in their bed sheets. This is real data. You can actually just look for public data on mortality rates and reasons for mortality. So usually at the county level, they have to document what is the reason why somebody passes away. And there are, unfortunately, a certain number of people who have passed away by becoming tangled in their bed sheets. And for some reason, that is correlated with how much cheese people are consuming. So they are correlated statistically, and someone might misinterpret that as saying that cheese is causing people to die in this way. But that's not what this data tells us. This data just says that they're statistically related. We don't know if one is causing the other. Maybe more people are eating cheese to deal with the grief of people who have died because they tangled in their bed sheets. We don't know either way. We don't know if it's X causing Y or Y causing X. All we know is that X is related to Y. Now, another example here is that what if you saw a headline that said playing video games makes you smarter? Gee, wouldn't that be great, right? And let's say it's based on this data here, that the total revenue generated by arcades is positively related to the number of computer science doctorates awarded in the US. Now, we don't know if one is causing the other. All we see from this data is that they are correlated. We just know that arcade revenue is related to computer science doctorates, but we have no idea if it's the people playing more in arcades are going to get doctorates, or maybe people that are getting doctorates are celebrating by going and playing in arcades. We don't know that. We just know that they're related. Now, I'll give you one more as my personal favorite. Let's say that you saw a headline that said eating less butter can save your marriage. And it's like one of those, tips to have a better life or something like that. Let's say it was based on this data here, that it showed this data where the divorce rate in Maine decreases as per capita consumption of margarine increases. So the more people are eating margarine, which is fake butter, for lack of a better term, I can't believe it's not butter, right? They are eating more margarine as people are getting less divorced. So some people might say that, hey, if you eat, the more margarine you eat, meaning the less butter you eat, the less people are going to get divorced. So I can't believe it's not butter, and I can't believe it saved my marriage, right? Very cheesy in that way. Now, we just know that these two things are related. We don't know if one is causing the other. We don't know if people are consuming more margarine and therefore are getting divorced less because they're bonding over fake butter. Or maybe people are, going to marriage counseling, not getting divorced and celebrating by eating more margarine. That just sounds ridiculous, right? And these are ridiculous because the idea here is that just because two things are related does not mean that the relationship is even meaningful. It's similar to statistical significance. Just because two things are statistically significant, meaning that it was unlikely for us to find it, assuming the null hypothesis is true, doesn't mean that the finding, whatever it was, is important. Just like finding that two things are statistically correlated doesn't mean that the relationship is meaningful in any kind of real substantial way. And even less so does it tell us that the things that are related in a causal fashion. Correlation does not tell us anything about causation. Correlation only tells us that two things are connected to each other, that they are varying in a similar fashion. But if you want to determine causation, you have to use experimental means. You have to use something like a t-test or an ANOVA to determine causality. Correlation simply examines relationships. And so with that, we will continue on with correlations in our next video, talking about how they apply in the context of hypothesis testing.